Today's lecture is about using of the synthesis gas. So we take a look at reactions of synthesis gas, hydrogen production, methanol production of methanol, and also the Fischer-Tropsch synthesis to some extent this figure is from course textbook, and it's just the idea is that to put you in the big picture where we are at the moment. So we are interested in the use of synthesis gas, and here you'll see Fischer-Tropsch for producing of alkanes, hydrocarbons. These are commonly found in fuels, in gasoline, in diesel type fuels. Methanol, we have already mentioned that many times during the course. So it's the simplest alcohol and can be used as a fuel, although it has several other uses as an intermediate in petrochemical industry. Also, synthesis gas can be converted to hydrogen with the help of water gas shift reaction. And the raw materials we studied, or the gasification we went through last week. So basically the new thing related to the biofuels is that instead of using fossil-based coal or natural gas, crude oil, we want to use lignocellulosic biomass as the starting point. But now to these reactions and products. This picture is a collection of synthesis gas based reactions, and also methanol is a product, and it also includes on the right hand side these other chemicals that can be made out of methanol as well. But we are mainly focusing today on this synthesis gas to Fischer-Tropsch diesel and gasoline, and then slightly addressing how to convert to hydrogen and also to methanol. But this only illustrates that there are many other products that can be made out of synthesis gas and also out of methanol, and some of them are also or can be used as fuels. Hydrogen is very simple molecule, and however, it's very important in processing of biofuels and other types of fuels, and also some main uses for synthesis gas derived or based hydrogen are ammonia synthesis, and this is something that it's used to make nitrogen based fertilizers, and it's very important process or industrial process, the ammonia synthesis. We are not going to address that today, but in today's world, when the world's population is growing and we want to grow more and more food so the fertilizers play a role, and the foundation of synthetic fertilizers is usually ammonia-based nutrients that are made out of hydrogen and also from nitrogen. Also, we have already touched during this course some reactions in the petrochemical industry and oil refinery where hydrogen is used in various reactions. I think one example is different hydro treatments that aim to remove some unwanted impurities from the product. Examples being for sulfur, so there is hydro desulfurization, or like in the conversion of triglycerides, so we removed oxygen atoms or oxygen functionalities from triglycerides with the help of hydrogen. So this is kind of important reactant in addition to the biomass derived components like the triglyceride or sugars or some other raw materials. I have taken this graph from an older website, but I can still show it to you because there are, personally I have used it because it contains this easy to understand simple information about many of the things that we also studied during this course. So the essential chemical industry online. So one can find, for example, here basic chemicals, listing quite many chemicals, some of which we have already touched during this course, but here is quite a nice list of different things related to that. Let's take methanol, for example. So here are background information and lots of other. You'll notice that this I have used also in some of the slides, but often here is, well, this was not very long, but there is a lot of material also about potential, like, let me take another example. Perhaps this ammonia is here. So something about the production volumes, manufacturing. Here's about manufacturing of hydrogen itself, reactions, and so on. About the Haber process and so on. But like this is condensed enough. So if you want to check something also about different reactors and green chemistry, also here are some pages about biofuels, biorefineries, and so on. So just as a recommendation, that place where you can find useful information. So coming back to the hydrogen, so it's produced in quite large quantities per year, and I think this number is already 10 years old. I don't have the current figure, but certainly if I have to make a guess, so the amounts have increased instead of decreased. And half of it goes to the ammonia process, which has been running nearly for, I think, from 1930s, so not nearly 100 years, but almost, not very far from that. Then refinery processes, these also include, I would say, nowadays the biorefineries and so on. Then methanol, and about 20% of hydrogen goes to various different uses. One possibility to make hydrogen is the water-gas shift reaction. And I think during these other courses that you might attend, so there is as an example, so electrolysis of water is one where quite a lot studied reaction or technology for making hydrogen. But this is the older reaction or process that typically was made based on fossil-based materials. So you have synthesis gas, and then you carry out the water-gas shift reaction, and basically you can increase the amount of hydrogen in the gas mixture with the expense of carbon monoxide. So carbon monoxide levels decrease and CO2 and hydrogen levels increase. This can also be used as a purification. So if you want to get rid of carbon monoxide, so that's could be possible. So there are two consecutive reactions. First with high temperature with iron oxide based catalyst, and the second one with lower temperature and a different copper based catalyst. And these figures have been taken from the course textbooks. So carbon monoxide drops to few percentage in the first stage, and after the second low temperature water gas shift reactor, it's already somewhere much lower, like it goes to 1/3 of the original amount. This from the simplified picture from that textbook. So you'll see here the gasification of, let's say, biomass or switchgrass, and the gas that is obtained from the gasifier. So there is already hydrogen and carbon monoxide, and that mixture we tend to call the synthesis gas. But there is also, like from the gasifier, you get various different gases. Here, carbon dioxide, methane are examples, and also the tar that we discussed last week. So there is a first step to remove the tars. Then the reformer is basically boosting the levels of hydrogen and removing to some extent methane. So that reformed gas mixture enters this high temperature and low temperature water gas shift reactors. In each there are these catalysts that were already mentioned, and eventually you get gas mixture that is very low in carbon monoxide and has a fairly high amount of hydrogen, carbon dioxide, and also some methane left. This was example from the course textbook of how to, let's say, or which steps might be needed for making this hydrogen out of biomass. So there are already like five steps here, and this is to some extent simplified version. If you want to get pure hydrogen gas, so you also need to remove carbon dioxide and methane. So this is not like ready as such. Hydrogen purification can be done with different techniques. I will not present these in the slides with much more in detail, but there is so-called pressure swing adsorption that helps to purify the impurities from the hydrogen. Also air oxidation of carbon dioxide, so basically removing CO, oxidizing it to CO2. And if there is a requirement for very high purity for the hydrogen, that can be obtained with this kind of membrane filtration. And palladium is a noble metal that is used as a catalytic material, but it has a special feature that if there is a thin layer of platinum metal, so hydrogen has tendency to diffuse through that metal film or layer, leaving everything else on the other side. So this is an expensive but used way to get the high purity hydrogen for research or other applications. Few words about methanol. Not very much. It's an industrial process, and well, this is from the same chemical industry webpage that I showed you already. Synthesis gas is reacted with on the catalysts and to produce methanol, and here is some 200-300 degrees Celsius and 40-100 atmospheres of pressure. The net reaction is the number 9 here that you'll see. So carbon monoxide and 2 hydrogen molecules react to form 1 methanol molecule and 1 water molecule. And you also release energy in this process, so this is exothermic reaction. If you want to get more out of this methanol chemistry, so can try to end this slide. So do I still have this open? Let's see. Was here something? Well, here is basically listed the various applications of methanol. So the main volume-wise product is formaldehyde that is then also converted to other products. But here you'll see, for example, petrol blending. So this can be added methanol into gasoline. Also biodiesel production. We are talking about the fatty acid methyl esters. So the methyl ester comes from methanol, and that is needed for biodiesel. Also these ethers of methanol, so methyl terbutyl ether and so on, are made using methanol as the raw material, and these are used as blending agents in fuels. Once the methanol comes from a biomass, so this is a bio component in the fuel. Also, maybe in the introductory slides, in the first ones for the course, I mentioned this dimethyl ether, which can be used as a fuel, and of course you can make it from bio-based materials. So in each of these, the methanol itself is the other starting material or raw material. I think yeah, well, there was not much more in here, but in any case, so methanol is a versatile chemical, and it has importance in making also bio-based methanol has importance in the biofuel production, and also it's fuel by itself and so on. Here are some production volumes, and okay, I didn't remember that the same picture can be found on the slides already, so we don't need to go through this second time. This picture is quite old. I showed in some of the lectures we briefly addressed that the methanol is a liquid fuel, and some shipping companies are converting their boats or ships so that the traditional diesel engines can utilize methanol as a fuel. But I think we don't need to dig deeper into this. There are examples of methanol use as fuel as such, or it's as a blending agent. Methanol is challenging if we compare regular diesel or gasoline, which is purely hydrocarbon. Methanol is alcohol, and there are some problems coming with that, which have to be overcome in order to use it as a fuel. This is maybe not very different from gasoline, so those are also toxic, flammable, and explosive. So that applies to gasoline, petroleum, as well as to some extent diesel. But what is very different is that alcohols are corrosive to common engine components. So they tend to corrode some of the material in engines, which otherwise tolerate very well hydrocarbons, so diesel or gasoline. And at least I heard an example that if you have an older vehicles that have been manufactured in, let's say, before 1970s or 1980s, so at that time alcohols were not added in fuels, So the fuel system, starting from the fuel tank into the engine itself, so contains, let's say, tubing or membranes or this kind of gasket materials that can corrode because of these alcohols. Also, fuel pump membranes can be broken because of methanol or ethanol in these older vehicles, but nowadays these have been taken into account, so that's not the big problem. Regarding lubrication, so methanol tends to be chemical wise different than the hydrocarbons, and also the lubricants that work with regular hydrocarbons do not work that well with methanol. Methanol dilutes them and dissolves them more, and there is the metal surface contact is not that well lubricated necessarily. Last one worthwhile to mention is that alcohols, this smaller alcohols, methanol, ethanol, propanol, to some extent butanol, so are water soluble. Methanol and ethanol are water soluble in all proportions, and with this, so they tend to cause problems during the storage, and also to some extent they can increase corrosion. But there are challenges, but this info is maybe, well, future use. So from renewable sources, so methanol can be converted to olefins. So that would be making of bio-based plastics. If the methanol is bio-based, it can be converted to gasoline components and it can be used as a fuel. So these have been now mentioned already quite a few times. But the key point maybe here is that from renewable sources. So methanol is a methanol production is very old and traditional, and it's important chemical, but now the transition has been towards renewable or bio-based sources or materials. So that means that the very same methanol is still used, but it's not made from natural gas or coal or crude oil, but it's more preferred made in these different biomass and waste fractions that we have covered during the course. Here, if you are interested in these other quite many that you'll see in the picture, these synthesis gas reactions and products, so you can study this. There's plenty of material in different core in this course book, and also in the materials that I have linked during the lectures and so on. We will still cover the most important or interesting synthesis gas application, and that will be the Fischer-Tropsch reaction or Fischer-Tropsch synthesis. And I think that's something that I will talk after the break. So I'll have a 15-minute break and we'll continue after that with Fischer-Tropsch synthesis. All right, let's continue with Fischer-Tropsch reactions or synthesis. The inventors of this reaction have been German, I suppose, German gentlemen who lived somewhere, or they made their discoveries in the early beginning of 1900s, so 20th century. And some numbers about the Fischer-Tropsch synthesis industrial history. So the reactions were, or the inventions were made in the 1920s, and these two guys discovered that synthesis gas can be converted into hydrocarbons, and it took over 10 years to make a first commercial plant, and a little bit later on it was running with 8,000 barrels of hydrocarbons per day. Slightly later, in 1950s, so Fischer-Tropsch production plant was also established in the United States. And after that, so I could guess or imagine that there has been since 1950s, so also the oil refinery processes and petrochemical industry started to dominate. So the Fischer-Tropsch, I would guess it didn't take so many steps, or it didn't grow so rapidly after this early start. I also already mentioned like that Germany was using this Fischer-Tropsch process to produce fuels, because during the Second World War, so at that time they didn't have access to crude oil, so they had to use their coal reserves to make fuels, and this reaction was the key to that. The other parts of the world had access to oil, and they, in my understanding, they didn't use the Fischer-Tropsch in process so much because it was cheaper to make fuels from crude oil, and they preferred a cheaper alternative. So it's a very simple explanation. Why the South African oil companies Sasol why they were interested in this Fischer-Tropsch was also the same background, that due to this apartheid and some restrictions in access of crude oil, so they had to figure out other ways how to make fuels. Fuels have always, at least for the last 100 years, have been the key to all sorts of human activity. So they made their gasoline and diesel fuels using this Fischer-Tropsch process, not from crude oil, but I suppose from coal, the same as Germans did. And later on, then this process got interest from other parts and from other aspects. So like Shell and so on started to there was not anymore this restriction to crude oil, but there were other things, like maybe there was a lot of cheap natural gas or something that could be converted using this technology. But the overall reaction is fairly simple. So we have synthesis gas, carbon monoxide and 2 hydrogen molecules. They convert to hydrocarbons. So this is the main ingredient in all the fuels. You will get also a water as a product. This is the overall reaction. Here are the other reactions that can take place during the Fischer-Tropsch synthesis. And here are the alkane production and alkenes. So these alkenes have double bond, alkanes have only single carbon-carbon bonds. Then since there are these chemicals, carbon monoxide and water being formed, so the water gas shift can take place. This was already discussed a little bit in the connection of making hydrogen. Here, side reactions are listed: production or synthesis or making of alcohols. So here it's drawn in a little bit strange way, but here is the hydrocarbon part and here is the alcohol part. So this is alcohol, and depending on how many of these CH2 units, so you have methanol, ethanol, propanol, and so on, longer and longer hydrocarbon chains, and then the alcohol. And also so-called boudoir reaction can happen. I think this basically converts the carbon monoxide into solid carbon and carbon dioxide. But the thing, this is one possibility to couple like carbon and hydrogen so that there are no oxygen functionalities. So that's the main idea, to get these desired products. Fischer-Tropsch synthesis produces always quite a complicated mixture of products. So this is kind of the reaction is kind of, one can illustrate it as a polymerization reaction, in that sense that this reaction, that the carbon monoxide and hydrogen combine, so they make just this one unit, but they can combine again over and over, and they make longer and longer chain products. And this is what the right hand picture illustrates. So depending on the probability of chain growth, so that is like how probable it is that the monomers keep on adding to the chain. So the higher the probability, the longer chain materials you obtain. So here this C20 plus means that when you approach the probability of 1, but of course that's not, you will never reach it, but close to that, so you get very, very long hydrocarbon chain. And this is good to note that gasoline and diesel are somewhere in the middle here, and you want only those. So you don't want the 2 short chain ones, you don't want the 2 long chain ones, if you aim for gasoline and diesel. So this method produces as such quite large amount of byproducts or side products that are not ideal or wanted. But there are techniques that you can go around of this. So this was the you can always optimize the process, so you can develop better catalytic materials and tune the for example temperature and how the reactions are carried out. That can help a little, but here's one possibility that you actually overdo the Fischer-Tropsch synthesis. So you aim for these very, very high hydrocarbon chains. So you work with this high chain growth probability. And then you basically do apply for, so then you get long chain waxes and hydrocarbons and you do catalytic cracking on them. So the cracking can be done in more controlled way so that you will get the desired gasoline and diesel hydrocarbon fractions out from it. So this is like the way that some Fischer-Tropsch plant operate. Okay, so it jumped here. Some numbers how efficient this particular process is in making of converting biomass into the fuel component. So the following table describes two parameters: process thermal efficiency, and the definition is here so that it's the energy in the fuel product divided by the energy in the starting material, the biomass. And the closer to 1 this is, the more efficient the process is. And then the more demanding is the so-called life cycle thermal efficiency, which incorporates this process thermal efficiency plus it includes energy losses required for growing of the biomass, transportation of the biomass, to make the process machinery and to let's say produce and transport the fuels and so on. So it takes more this cradle to grave ideology, that it includes more aspects into the efficiency. And here are some of the numbers. So the fossil natural gas based so synthesis gas to hydrogen process is very efficient. So 83% process thermal efficiency. So majority of the energy in the natural gas will be also in the product hydrogen. If we use coal to make hydrogen, that efficiency is roughly half of that what is with natural gas. And here the readings vary quite a lot. So if we make hydrogen out of biomass, so we are not as good as from natural gas, but it can be reasonably high. And the other things are also that if we use biomass and convert that to Fischer-Tropsch liquids, so the efficiency can decrease quite a lot. So it's from the biomass to hydrogen process, maybe half of that again, and so on. But in any case, so this explains partly perhaps that because this process thermal efficiencies are lower, so already in that sense though, so it's expensiver to make the fuels with this process than if you make them from fossil-based natural gas or crude oil or coal. But that's something that we want to avoid. I haven't checked, but there is a YouTube link to the South African oil company's Fischer-Tropsch process. So I will probably not play it during this classes because there are this most probably some advertisements coming. I don't have the paid version of YouTube here, so. But if you are interested in getting additional info, so take a look at that. This is kind of an overview of the FT synthesis, and there are two possibilities, so low temperature process and a high temperature process, and there the products are slightly different, which is understandable. So if you use the temperature is one parameter that can change the outcome of a reaction. So of course, if you use higher temperature, already the thermodynamic equilibriums are different than at low temperature, and one can expect to get different products. But then also there are different catalytic materials developed for these two different processes. So high temperature works with fused iron, while the low temperature ones utilize cobalt and precipitated, so slightly different way, prepared iron catalyst. Here at low temperature regime, you might use slurry or fixed bed reactors, while the high temperature process, according to this material at least, uses the fluidized bed reactor. Seems that the low temperature iron-based fixed bed catalyst reactor has been used longest. So here is pre-World War II until today. So the latest developments are these slurry and fluidized bed reactors for that Fischer-Tropsch synthesis. Let's see. These slides are not all in logical order, but try to cope with me in any case. So here are some of these main reactions and side reactions again. I think these, but in any case, so what is wanted are the olefins. So this could be used to make polymers, so polyethylene, polypropylene, and such kind of important materials. The side reactions cannot be avoided because, well, at those conditions, and when these products or chemicals are there present, so they tend to happen to some extent. You can try to avoid it by tailoring the catalytic material or tailoring the operating conditions. But Yeah, we went through already this, that water gas shift can take place. Also alcohols can form solid carbon materials, and of course this catalyst can undergo also reactions like reduction and oxidation, depending on what type of chemicals are available. And the coking is also one type of solid carbon, so that's also was the product in the gasification, depending how it's operated. This is maybe a key picture to figure out, like from that Fischer-Tropsch reactor. So under the standard is not saying much. It's certain typical operating conditions. So what you get out as a product, so this is the distribution of those hydrocarbons, and you'll notice that the gasoline, what is one of the main desired products, so you should be there like between roughly 4 to 12 carbon long hydrocarbons. If you want diesel components, so then it's like from 12 to slightly somewhere close to 20 or 22. And what I mentioned, that some facilities prefer to do the products through the waxes, so they prefer the longer hydrocarbons, and then they crack those in a second process to these desired shorter chain materials. Jet fuel range is here like from somewhere from 7 to maybe 16, something like that. But just to get the idea that when you do this, so you always end up with this type of distribution of products. So you cannot only have the diesel products, because you always get other products in addition. Also the one carbon, so methane is produced in this method as well. What you get out is olefins. So that I mentioned that these are probably not converted into fuel components, because one can make plastics out from these. But paraffins, so these are the typical components in diesel and gasoline, and those are the ones. Oxygenates, so this would be the oxygen containing components that are added into fuels, and examples of those can be the MTBE, so the ether type components. I'm not sure if you get ethers from Fischer-Tropsch, but it was mentioned that alcohols are formed, so ethanol can also provide oxygen into the fuel. Branch components, so these are like branched hydrocarbons, and from that high temperature process you can also, according to this, get aromatic components, so like these benzenes and toluenes and xylenes and such type of materials. I will not you don't need to study or understand this. It's this catalyst production process, but here are just like those three different types of catalysts. So the catalyst manufacturing steps are described here. So what is difference between, let's say, precipitated iron and fused iron? So the catalyst production is different. It says that this fused iron catalyst is the cheapest, and it works well in the fluidized bed reactor. So these starting materials are mixed and heated in 1500 degrees in the presence of oxygen. So it oxidizes, forms this iron component, which is basically cooled rapidly and crushed into suitable particle size, and that is the catalyst that works well. Precipitated catalysts are made so that you mix the precursors and then you do some kind of change, like typically you'll change the pH of the mixture so that at the starting pH all these components are soluble to the mixture, and after change of pH they'll precipitate out, and that precipitate solid material is then washed and dried. Calcination refers to heating it up in the air. Typically it can be quite high temperatures. So here, for example, this heating in air and 1500 degrees, so can be understood as a calcination step. And after that you get a solid material that contains the iron, catalytic iron, and the support material. Then the last type of catalyst here is cobalt. So these two previous ones contained iron atoms or as the active catalytic ingredient. This contains the cobalt metal, and that's supported on certain support materials like silica, alumina, zinc oxide, or titanium. We touched these materials and different types of catalysts earlier, so this should be somewhat familiar to you. So it's very common, like here, this you adsorb or like impregnate, like in here with the cobalt salts. This can be probably soluble to water, but the solvent can be different. So you impregnate the support, then you dry it, then you calcine it, and then you convert usually the cobalt into some other form, like not this cobalt nitrate, and probably cobalt oxide. And then you have obtained the actual working catalysts. This table collects the, let's say, benefits or properties of these different type of catalysts. And iron is cheaper than cobalt. Also, you'll notice here that cobalt doesn't catalyze the water-gas shift reaction. However, in iron catalyst, it's notable. So the water-gas shift happens. Then iron catalyst, I don't know what is meant by flexible, but it's more than a cobalt material. Sulfur tolerance it's similar, but in any case, so very low levels of sulfur are needed. And I could imagine that the sulfur basically deactivates or kills the catalyst. So that is the problem. No, it's not due to the sulfur dioxide emissions or such. It's problem for the catalyst. The mechanical strength of the catalyst is this attrition resistance. So the iron is not mechanically very strong, whereas cobalt on the supported cobalt catalyst is. Here are some examples of the commercially used reactors for the Fischer-Tropsch synthesis. So I think it's not that important to study these in detail. If you are interested in these, so I think there's a video on the next slide. No, it's not, it's that one. So here is it's not very fancy video, but it explains these common types of Fischer-Tropsch reactors and what is the main working principle in the reactors. And again, it's in the YouTube, so I will not play it because I don't want to record the advertisements. So fixed multi-tubular fixed bed reactor, circulating fluidized bed. Then there are fixed fluidized bed and fixed slurry bed. But the same type of reactions take place here. Each of these contain the catalyst material, and also the reasons why there are different types of reactors so can vary. So it can, like mentioned here, so here is some kind of technology development taking place. So like this tubular fixed bed reactor is very old, but it's still used. But for example, the slurry phase distillate reactor is rather new and so on. So the reason for different types of reactors can be that some of these reactors have some patenting issues, and the competitors cannot or don't want to use them or pay the license fees, or they have invented something new that suits better for their purposes, for their production facilities. So they have made like improvements in the process, and therefore they are using a different type of reactor. So but this type of, if you make a Fischer-Tropsch factory or industrial site, so it's something that you don't, the reactors are quite large and expensive and with all sorts of upstream, downstream equipment coupled to it. So you will not change these every year. So you tend to run these facilities once built for tens of years. So that could also be one reason that certain factories have different technologies, so that everybody is not using the same production process for making these products. So what I mentioned, so if you are interested, take a look at this. I checked that it works still. So it explains about these 4 types of reactors, their properties and benefits, disadvantages. This is not process technology course, so in that sense there is no point in focusing very much on these different types of reactors. So the idea is that you just understand or get kind of a glimpse that the different companies have different types of processes that are fundamentally the same, that the chemistry is roughly the same, but the hardware, the setup can vary quite a lot. But they use the catalyst and the Fischer-Tropsch reactions to make products. Yeah, this is what I said, that these are in a not so logical order, because now I have few slides again about the different mechanisms of Fischer-Tropsch polymerization reactions. But for generally for polymerization, so there are these chain initiation, chain growth, chain termination reactions taking place, and their relative rates are basically influencing what type of products come out from that process. Here, not all polymerization processes are heterogeneously catalyzed, but these are now heterogeneously catalyzed, and that means that the catalyst that we just looked a few slides back, so those are all solid catalytic materials. So we talk about heterogeneous catalysis, heterogeneously catalyzed reactions. And that means that everything happens on the surface of the material, and all the reactions start from adsorption, so that the reacting components come in contact with the surface. Then there can happen different things. There can happen dissociation, so that the molecule breaks or changes the form. And then there are various mechanisms. I'll show you few slides some of the mechanisms. It's, of course, these reactions are not fully understood how they happen, but there are certain researchers propose a mechanism which fits certain experimental data. But basically the reactants come in contact with the catalytic material, the chemistry happens on the surface, and once the product is formed, so it desorbs out from the catalyst, and then this so-called catalytic cycle happens again and again and again, and new reactant molecules are converted into product molecules. The desorption step is crucial for catalyst, so that if the desorption would not take place, so then the product would stick on the surface, and very quickly it would cover the whole catalyst, and that would be called this deactivation. One type of deactivation is that these very strongly adsorbing materials stick to the surface and will never leave the surface, so that's they basically make the catalyst inactive, because nothing else can access the surface after a short while. But here, here are this initiation step is basically something like when the intermediate is formed on the surface, the chain growth step are these that go from top to bottom here, that you notice that the chain is growing. So one carbon turns into 2 carbons, into 3 carbons, and so on. And these ones on the right-hand side are the reactions that combine with hydrogen and make these hydrocarbons, these alkenes. And the left-hand side are those that don't combine with hydrogen, and those are those so-called olefins that contain these double bonds. I think I will not go this into detail. Basically, here are the same steps up here, and the left-hand side is for the synthesis gas, the carbon monoxide. The right-hand side contains like the hydrogen adsorption. Here is the carbon monoxide adsorption, and but it's not. I'll consider this too detailed information for this particular course. But the straight line and the letter M, that refers to that catalyst surface. So like this is highlighting that everything what happens takes place on the catalyst surface. Then if we go into details of these different types of proposed mechanisms, so there are several of these, and again I think it goes a little bit too deep into the topic, but it's maybe good to know that there are some of or many reaction mechanisms in that Fischer-Tropsch reactions. And these I will not cover, these mechanisms step by step. But here we can stop for a short while. So this ASF plot is so-called volume Anderson-Schulz-Flory distribution. So it predicts how long hydrocarbon chains or how long polymers are formed in this type of reactions. And here the alpha refers to the chain propagation, and beta refers to the stopping or the termination of the propagation. Like this is illustrated on the right hand plot here. So there is the probability is alpha for the propagation, and then 1 minus alpha is the rest is the termination probability. That's here in this left hand side, it's referred as beta. But with this type of simple mechanism of the one can predict the product distribution to some extent. So again, not going through this much in detail, but there is just this parameter that the probability, chain growth probability, that can predict how much of different carbon length products you will get. The n, small n here, it's the number of carbons, and the alpha is the chain growth probability. And the Wn is the weight fraction of n carbon containing product. So if you plot this, you'll get these graphs that you already, I think I showed you this already, but not these. So here, what is the difference is that the alpha, the chain growth probability varies, it increases, and you'll notice that this selectivity to different hydrocarbons. So with the higher higher alpha value, so you get more of these longer chain polymers or more products. This graph contains this similar information, so that with different chain growth probabilities, so the higher the probability, more you get the longer chain material. I made a long time ago already this type of Excel illustrating this same. So here is the basically on the yellow background, this is the alpha, so the probability, chain growth probability. So what you will notice here, this is only limited to 20 carbons. One could of course extend the graph longer and longer, but the idea is that if the chain growth is increasing in probability, so you'll notice that now there is just methane and ethane based products with a low chain. If you increase it, so you'll get a little bit more of these 5-6 carbon products. If you increase it to further, so you start to get lower amounts of methane. The maximum amount is like 3 carbon products, and then you already get some 20 carbon products as well. And then when you go increase this further, so like in those graphs, so this maximum will shift towards right, towards higher carbon values. And when it's like close to 9, so you start to get less and less these shorter chain hydrocarbons and more of these higher ones. Now that the graph stops at, or these values stop at carbon 20, so this would of course continue like here. So, and if I would increase this closer and closer to 1, so then it would keep on shifting towards the higher carbon lengths. But this same type of graph it comes from the polymer chemistry. So if you are interested in, so take a look at textbooks of polymer production. So there you might find more about it, or of course textbooks of Fischer-Tropsch reactions. What else I still have? I think I will not keep an additional break, but we'll continue. This was from the older slides that I had, so I was just we have not talked about reaction kinetics or kinetics, and it's not really very important, but the rate of the reaction, or this is the rate equation, and it tells that if you have different catalysts, iron or cobalt based, so the reaction rate depends on different parameters in a different way according to this equation. And it was mentioned in the table that some of these catalysts are, for example, sensitive to water gas and some not, and so on. But the key thing here is that at these, although it's the same chemistry, so the rate equations are not mathematically the same. And I have listed here some of these key things, but I think it's again not that important to understand them deeply. But here is like what you see here is that on the nominator, so you have pressure of reactants here, so pressure of hydrogen and pressure of carbon monoxide. The same with the cobalt, but the denominators are different, and that influences how the system responds to, let's say, changes in the pressures of carbon monoxide and hydrogen and water. And in principle, here you'll see that in the denominator here is not water, whereas with that iron-based material here is water. So these catalysts or the systems respond differently into amount of water. This cobalt is independent on water. So basically, I think it was mentioned in the table here that, let me go backwards. No, it was somewhere else. Was it in the... Sorry, I thought that there was mentioned that they... No, it was this water gas shift, yeah. So the cobalt, there is negligible water gas shift, and iron is significant. Okay, I thought that it was related to water, but is... Yes. So in short, so reaction rate and how the different catalysts behave. So it's those behave differently, and one can utilize it as a benefit or disadvantage depending how the things work. And here are some dollar readings about the Fischer-Tropsch economics. I think these are taken from the course textbook. So but I will not go into these details. I'm certain that these numbers are not, one cannot take them as certain in that sense that also this Fischer-Tropsch is very much dependent on many things, and if you compare with the fossil-based materials, so those prices vary quite a lot. So don't take these absolute dollars as a truth. It's just maybe order of magnitude at this particular time when these numbers were calculated. The cost distribution is maybe more relevant for this particular course. So this NTL refers to the fossil-based, so natural gas to liquids, and BTL is biomass to liquids. So how much comes from the natural gas? So one quarter. What is this is difficult for me to read for some reason. So one quarter comes from the raw material cost. One quarter from the operational costs, and 50 is the capital investment, what has been invested in the hardware. Here is case number 2. It has slightly different percentages. There are so many numbers that I'm just trying to look for in some comparison, but actually difficult to conclude. I didn't notice while I was preparing these studies. So if you think here that you start from biomass, so wood or something, so about 1/5 of that cost goes into the pre-treatment. It was mentioned already previous week that pre-treatment step in the gasification can be the most expensive one. Then 18% goes for the gasification, and roughly the same amount goes for cleaning of the gasified product. 15 for making of oxygen. One very little goes to the water gas shift reaction to make this synthesis gas, and actually only 6% goes for that Fischer-Tropsch conversion, and so on. So if you compare, so at least the biomass to liquid process has more steps than the natural gas to liquid. So here are only or are missing the biomass treatment and so on. Cleaning steps are different. But yeah, this syn crude upgrading is maybe the last slide that I have about this. So it means that we have talked so far about the Fischer-Tropsch synthesis, and when you get those products, so we noticed that there are a lot of different hydrocarbons coming out. So when you have this complicated mixture of products, so those cannot be used as such. So then you need to extract some wanted products and purify some feeds. Hydrocracking can be done for those very long chain materials. So you cut them, crack them into small shorter chain liquid fuels which are wanted. Oligomerization, you can convert the olefins also to fuels if you want, if you don't have polymerization plant where you can make plastics. You might need to do alkylation, isomerization, aromatization reactions. If you want to upgrade them into plastics, so then you have a ethylene or propylene polymerization plant, so that's also a possibility. Or you can carry out hydrogenation, so this one type of hydro treatment where you reduce this refers to promoted fuel stability, so you want to reduce the ethylene and the double bond containing components in the mixture to make it more stable. The polymer double bonds are much more reactive than single bonds and aromatic bonds, so you can convert double bonds to single bonds with the hydrogen in the hydrogenation process. But these are kind of different processes, so you will not do all of these in a Fischer-Tropsch synthesis unit, just some of them. Of course, extraction and purification is probably done, like separation of these, but you will not do always like hydrocracking and polymerization and hydrogenations. Those are kind of alternative possibilities. Because the Fischer-Tropsch reaction and processes have very long history and so on, so there is a lot of material available. If you are interested in studying this further, so this still exists, this fischertropsch.org, and there are links to very old materials, very research reports, and all sorts of plentiful of materials related to Fischer-Tropsch processes. You can find books and well, review articles as well. But this reaction in summary, so this reaction has kind of been active more or less hand in hand with the oil refinery and petrochemical industry, and it has always been slightly more expensive than what were the products from oil refinery. So unless there is something unusual, so this has not been very popular. So Germans used it because they didn't have access to oil. The same one was South Africans. They used it because they didn't have access to oil. And now the new, let's say, interest stems from the fact that we want to get rid of fossil-based materials, and this offers a possibility to make similar hydrocarbons from biomass with that Fischer-Tropsch technology. So this is maybe the reason why this now became more interesting than maybe ever before, this Fischer-Tropsch chemistry.